So, in the last class I have told you how to classify materials based on applications. You can also classify materials based on bonding. So, the second type of classification that we talk of is related to bonding. So, how many types of bonding you are aware of? Please write in your notebook. Primary bonding in particular and the class of materials that you are aware of. So, this one of them is going to be metallic bonding. Metals are supposed to possess metallic bonds. Ceramic materials are supposed to have ionic bonds like sodium chloride. And the names of the metals that I have already told you, they are good metals like gold, silver, copper, aluminum. They all have metallic bonds. Now you come back to polymer. Polymer has got combination of two types of bonding. One of them is covalent bonding and there are some secondary bonding as well. They refer to van der Waals bonding and hydrogen bonding. Polymers have a serious limitation and that refers to its biodegradability. In contrast to that, metals can be recycled. That's not true for polymer. In many of the cases, you will not be able to recycle it without costing environmental pollution. So that's the serious limitation. However, you cannot survive these days without polymer. Take example of the classical polymer, the tire itself. There is no substitute for that. So you have to go ahead with it, tire, right? Then the fourth class of material that people talk of, but it is not based on the bonding, rather a type of mixture known as composites. Composites are basically a combination of two materials so that you can exploit the best properties through the combination of the properties of the two. Composite materials are the kind of inventions that the mechanical engineers have done for us, right? They started combining it. They were disparately looking for something where the strength should be there as well as the possibility of making a component should be also there. So, one of the example of the composite materials I give you just for illustration is the fiber reinforced composites, where fiber is normally a ceramic material, for example glass fiber, and it has got a matrix and that matrix is polymer based matrix. So, this is the reinforced plastics. Normally, in short, you call as FRP, fiber reinforced plastics. You know that the best, lightest and the most stiffest of the material that people are thinking about for the rocket nose refers to carbon-carbon composite, where carbon behaves in one form as the reinforcement and another type of carbon known as the pitch that you see on the road, quality pitch, that is just like your polymer. So, carbon-carbon composites. Because as you know that in all aerospace industry, the density is very, very important. So, the density must be low. Carbon-carbon composite really qualifies that. Therefore, people are talking about that this class of material is going to be the material for aerospace applications. Now, in metallic case, you are in a position to appreciate based on the learning that you had that it has free electrons. What is a metal? Metal must have free electrons. And what is the proof that metals have free electrons? Because it is a very good electrical conductor. And the conductivity of a metallic component, electrical conductivity in particular, is going to be decreasing with respect to temperature. Is that correct or not? Resistivity increases with respect to temperature. So, any material which has this characteristic, that means you are definitely dealing with a metal. Last time, remember, I was trying to tell you that if you try to look at the sound after beating a metallic piece, it has got a metallic sound. That's not enough, because that's not a quantitative analysis of knowing whether you are dealing with a metal or not. So, you can measure resistivity of the material and finally come to this. Can you guess a kind of material where electron conductivity could be there, but the resistivity is reciprocal of that of temperature? Can you guess? Semiconductors. Now, you come back to the bonding, nature of bonding. Do they have metallic bonds? No. Silicon, germanium, they don't have. So, therefore, we are correct in assessing that really metals will have free electrons and the resistivity is going to increase with respect to temperature, and that is a sure shot proof that there are going to be some metallic character in the material. Now, the next question is that can you manipulate the property of a material? That is the next point. So, how are you going to do it? Let us keep guessing it. But one of the central point of this question revolves around a very, very classical relationship in materials, science and engineering of materials, where you can manipulate property of the material by controlling structure. So, what is meaning of structure now? So, now we are trying to discuss what is meaning of structure. So, for civil engineering, the structure refers to a macro structure. Macro structures are those structures that you are able to see with the help of your eye. So, please write in your notebook how much we can see with the help of our healthy eye. Healthy eye. So you can recollect your high school learning where you have been told about the least distance of distinct vision, and what is that distinct vision? So you write that. Does it specify a distance? Yes. Distinct vision and the least distance are two different things. Are you able to see it or not? Distinct vision means that the two objects separated by a minimum distance are you in a position to see. That's the point number one. And the second point, that where to keep your eye to see that. So you must have a standard, and that standard is 25 centimeter. So I gives a wonderful example of a telescope and a microscope both. Distance of vision, distinct vision, is a parameter related to telescopic characteristic. Whereas, when you say that you are able to resolve the two objects that are separated by a minimum distance of x millimeter, then that x millimeter is the resolution of the eye, of the microscope, right? So what happens if I place an object, seemingly that object consists of two lines, for example, drawn in the proximity of each other in such a manner that it has got a distance of separation less than 0.1 millimeter. Obviously, you will not be able to see it with the help of your eye. Something that you cannot see with the naked eye, whatever nature has given us, then this structure refers to microstructure. And microstructure is very, very important for manipulating the characteristic of the material to yield desired property. So let us try to understand what does it mean. So can you tell me how much is 0.1 millimeter in micrometer? Please convert quickly. 0.1 millimeter in micrometer. 1 micrometer is equal to 10 raised to the power minus 6 meter. Yes. So how much micrometer is this? 100 micrometer. So anything, if two objects are placed less than 100 micrometer of separation, you will not be able to see it with naked eye. This requires microscope. Now, how many types of microscope you can have? Many. Structures are many, so is the case with the way to observe them. So now we come back to, so our heading becomes therefore microstructures, and we want to see it. an object with the help of an optical microscope. So, I want to see microstructure. With the help of optical microscope. We shall not be talking about telescope because astrophysicist and the student of physics will be talking about whenever they are referring to celestial object. We don't care for the celestial object in this class. So, we will mostly be going inward. That means finer and finer and finer and finer. And what is the limit of that fineness? We shall never go inside the nucleus. We shall never go inside the nucleus until otherwise specified. When we talk of nuclear material, then only, but in this class we are not going to cover anything related to nuclear material. So, you come back to optical microscope. So, please write down in your notebook average wavelength of visible radiation in angstrom, then try to convert it into micrometer. Average wavelength of visible radiation. Let us not waste our time. Hello, young man. If you don't like the class, you can go out. Now everybody will see you also. So, did you get a number of 5000 angstrom? Average will be around that. So, did you convert it into micrometer? Yes. How much is that? 5. And how much I was able to see? So, how do I see something of 0.5 micron? What is the nature of magnification that is going to be there? How do you go from 0.5 micrometer to 100 micrometer? How many times I should magnify? 200. Is this mechanical answer correct? No? So now I construct an example for you and you tell me that how much you should be able to see. Now I go one step further down, 0.01 micrometer. Please write 0.01 micrometer. You have just now said 0.5 micron, no? Okay. So 0.05 micron, let's write, so that the order of magnitude is same. Now how much time I should magnify? I give you an optical microscope having capacity to reach that magnification. So you will be able to see it. That exactly is wrong. That exactly is wrong. Is that clear now? So you will remember forever. So therefore, it is not the magnification that is important for seeing an object. Something else is also important. If you Keep magnifying, then you will be able to see everything that is not correct. What is your everyday experience? How do you say that? Mobile camera itself, right? Depending on our capacity to record an image per second pixel, right? There is a X camera, there is a Y camera, and you keep magnifying it. The best quality camera will not show the blurred image. Bad quality camera photograph, you will be able to see breaking of the pixel is diffuse. So therefore magnification is not important. And from your mobile, how do you magnify normally? How do you magnify? Normally for your parents, for example, or your grandma, if you have to show something, they will say, this is very small, can you enlarge it? So you take the copy and the best possible monitor that you have, you try to put it, and finally. And you feel very sorry for your quality of the image, because now at least it has been magnified. Depending on the size of the screen, you will be able to know, though you have magnified and there is a blurring of the image. Also, you can zoom it. So when you zoom, every time the magnification increases, but the picture quality of image also goes down. It's picture, young man. But if it is the details of the material, then you cannot afford to make any compromise, because you have to reach at the bottom of it what is there. Why? You have said that the structure dictates the property of the material. So you must know structure. So in optical microscope, therefore, there is a limit of resolution. That limit of resolution is around 0.2 micron. It is closely related to the wavelength of radiation. And what is the wavelength of radiation? 0.5 micron average. You have just now told me. And why this statement of ours is correct? The statement of ours is correct because there is a rule. And what is that rule? That is laws of nature itself. And what is that laws of nature? That you cannot see. And what is that laws of nature that you cannot see in physics? All laws of nature that you cannot see, but you see through equations, are either quantum mechanics or relativistic mechanics. So what is that quantum law or the postulates of quantum mechanics that tells us that now you cannot resolve it beyond the order of the wavelength of the radiation that you have employed. What is that? Uncertainty principle, right? And what does it say? What was the experiment that he conducted? What was the experiment that he conducted to arrive at that? The experiment. Experiment.
Showed light to a moving particle, and the light also gave it energy. So the position.
What was that experiment? I am referring to the Nobel lecture that Heisenberg gave. Optical microscope. Do you know why? The It is said that he was asked in the diploma physics examination, केवल नाम diploma है, standard is very high. So, this diploma physics examination, he was asked, what is optical microscope and the resolution of an optical microscope? Looks like people say, those who understand history of science, they say that he was unable to perform. So he started his Nobel lecture by saying, today I am going to tell you what is resolving power of a microscope. So this resolving power of a microscope permits us to arrive at the so-called mechanical expression that we mechanically remember, and it is related to resolving power of a microscope, right? And it can be shown without any difficulty that yes, resolving power of a microscope cannot exceed the average wavelength of the radiation that you have employed. Now, let us come back further finer. Now I want to see distance between the copper atom, right? Two copper atom and that distance I want to resolve. The distance between two copper atoms are supposed to be angstrom. So please convert 1 angstrom in micrometer. Right. I am not confident of what you are saying. 1 angstrom you try to convert like an algorithm, that this is how it is. Is this 0.5 micron? No. So how much is 10 raised to the power minus 4 micrometer? 30. Then only there is going to be 1. So what is the typical magnification that you will be requiring? Make it 0.1 millimeter. Right now you are in the micrometer. That has to go to first millimeter. Then you multiply it by suitable number so that this guy becomes 0.1 millimeter. Right? 1 lakh I think. It should be 1 lakh. So you just multiply it by 1 lakh. How much is that? It must come to millimeter, otherwise we will be in trouble. It should come. 10,000 onwards itself you should be able to see it, but very blurred image. By 1 lakh you should be able to see it. Does it come to 0.1 millimeter or not? So you have to go for the lakh of magnification. Can we do it with the optical microscope? We will be putting the objective, multiple objectives, very large objective. Can I do that? Can I do that or not? Why? Laws of nature. There is no other answer. If you keep arguing with me, I have to stop at that place. This is laws of nature. And once something is laws of nature, we don't challenge it at all, because nature doesn't know it, how to do it, against it. So therefore, you will not succeed. If you succeed, you are going to be in trouble. So follow laws of nature. So now, next question is that how do you see it? 1 angstrom. Can I employ electron? Can I employ X-rays? For copper target, the typical wavelength of copper is 1.54 angstrom. This is just a statistics. Since you want to see 1 angstrom or so, with 1.54 angstrom probe, you should be able to go to 1 angstrom level. But you will not be able to see any microscope related to 1 micrometer, X-ray microscope. You will not be able to see X-ray microscope. So you have to find out by tomorrow, because I have a class tomorrow, that why X-ray microscope is not there. But electron microscope we have, right? And this place is the historical user of the electron microscope in this country. We are the first to have used electron microscope on the campus. So what is the characteristic of wavelength? Next question. How can electron have a wavelength? Due to dual nature. So you employ de Broglie wave particle duality, and therefore you have electron although a particle, but it has got a wave character. Does it have a fixed wavelength like that of visible spectrum of light? No, it does not. It is sensitive to the velocity of the electron, that you force it to get accelerated. And how do you force a charged particle to get accelerated? By electric field. Suppose that if the electron is coming from that side, I will put a positive potential this side, all the electrons from the source will be running towards this, and this is what I want, that it should be running very fast. So how it is going to run very fast? I will keep the positive potential in this end more and more. So the electron will try to keep coming out of the source, normally known as the electron gun. Basically some kind of metals having lot of free electrons, so that given the opportunity, those guys will be able to leave the surface, right? So they are leaving the surface, and this side there is a positive potential, so it tries to come. So what I will do is that I will not permit this guy to reach here. In between I will be placing my specimen, and I will ask that the running electron, can you get me some information? Those electrons are running, they are coming, and finally interacting, right? If all the atomic layers are behaving in your specimen as some kind of grid, right? Grating. You remember the grating experiment? I am referring to that. उसी को मैं ग्रिड कह रहा हूं, grating, right? Grating at 1 angstrom interval, the electron is trying to come and hit it, and finally gives a interference signal. So you will be able to see, oh, there is an interference that is taking place of the order of 1 angstrom. Then you will be able to perhaps know that there are two gratings atomically sharp grating located inside the material at every interval of angstrom, and that is how you will be able to do this exercise. Then you have to ask the following question, that if this planar grating is not placed periodically inside the material, will I be able to see and predict where can I get the constructive interference? The answer to this question is no. You will be able to predict only when it's periodic in nature, right? Otherwise not. It becomes very, very complicated issue to predict, right? So this is challenge number 1. You should be able to see it and you should be able to interpret it. And interpretation is the most important part that is expected from all of us. All graduates are supposed to be interpreting the experimental observation, right, properly based on the laws of physics. Now, in optical microscope, the first level that you can investigate is microscopic. So, you can investigate up to micrometer of distance. Second, if it is electron microscope, then you should be able to resolve object of the order of an angstrom. If I can resolve object of the order of angstrom, that means I will be able to see where are the copper atoms inside my specimen. If I can see it, then I will be tempted to know that can I take out one of the copper atom and put some other atom at that place. That's the next. Is that correct or not? I will ask the copper atom that can you come out? I want to put another atom. Is that correct or not? And this is where we are today. If you have come to the class 20 years back, I would not have claimed it so. But today we are there. If somebody says that I give $1 billion to you, can you put my name with the gallium atom, R.K. Mandal? I will say yes, I can. So he or she has to tell that what is the tentative audience size and geographical location so that they all can see together. I will say yes, I can do it. Absolutely, there is no problem. This is known as engineering materials at atomic scale. That's the challenge, right? I do not know for the bulk production, but we will be able to do it. And whatever I am saying, this is already 20 years old, right? First time IBM people have done it, written IBM with, I think it was gallium atom only, if I correctly remember. It was with the gallium atom, IBM with gallium atom. So you should only appreciate what it tells is that I do not care for your thermodynamics. This nearly challenging that. See, I am yet to see a gallium structure where naturally in some domain I will be able to see IBM written at the atomic level. There is no way. But here is an example where the gallium atom people have put it in a manner that no gallium crystal has ever displayed. So, this is known as engineering materials, design of materials at atomic scale, that is possible because of the advancement made so far in electron microscopy. Looks like that we are already on the theoretical limit of resolution, and that comes out to be around half angstrom. So, you will be able to see exactly 0.5 angstrom. So, that is the kind of thing that you have. So, this length scale is also sometimes called as submicroscopic length scale. Submicroscopic length scale. All length scales less than a micron is known as submicroscopic length scale, and they have to be investigated with the help of electron microscope. And the grating that I have told you periodically placed forms the basis of crystal structure. So, I have told you the two types of classification based on application in the previous class, and today I have told you classification based on bonding, followed by we have posed a question that what is the purpose of this class? To know the structure and finally relate it to structure, and for knowing the structure we are supposed to see it, and for seeing you have to employ tools other than your own eye, and those tools were optical microscope and electron microscope. Okay? In case you have any question, you can ask so that I can answer, otherwise we will thank you each other. Question, please. So, shall we conclude then, otherwise? Okay, you can ask me tomorrow also, absolutely no problem. But please do ask so that I know what I have communicated. So, thank you very much. Thank you.